Welcome to qnawire.
Okay, so the way these problems are done is that you're going to need a table which shows you additive parameters for predicting NMR chemical shifts, right? So in the absence of that kind of table, there's really not much you can do, but I'll walk you through what the values might be from a table like that. First thing you need to do is figure out what substituents have what relationship to the proton, right? So this we consider the alpha position, the carbon that neighbors the carbon with the proton. This we consider the beta position, and this is the gamma position. Anything beyond that is unlikely to affect the proton. Next, we determine what the base value is for this proton based on whether it is a CH3, CH2, or CH. In this case, it's a CH3, right? It's a methyl. So the base value is 0.9. Then we look at what's in the alpha position. We say, okay, in the alpha position, we just have carbon, right? So we say that's like an R, right? So at the alpha position, if we have an R, the additive parameter is 0. Okay, so we add 0. Nothing doing. Okay, at the beta position, we have an oxygen that is an ether oxygen, right? So at the beta position, we look at our table and we say if we have if we have OR in the beta position, then we need to add a 0.3. Okay, and then we look in the gamma position. We say in the gamma position, we just have an R. Okay, so in the gamma position, an R's effect is 0. So we add 0 altogether, we get 1.2. Okay, not so bad. Let's do it again. So now we've got a hydrogen here. Once again, it's a methyl hydrogen, right? There's 3 of them here. Okay, so we're going to start at 0.9. This one's a lot easier, right? Alpha position is R, that's 0. Beta position is R, that's 0. Oh, wait. Sorry, damn it. Oh, no. Yeah, this is correct. Okay. Alpha position is R, beta position is R, and gamma position is R. Perfect. Okay. And it turns out that the effect of an alpha position being an R is 0, beta being R is 0, and gamma being R is 0. And we don't actually have to worry about this oxygen at all because it's beyond the gamma position, right? So 0.9 plus 0 plus 0 plus 0, well, that equals 0.9, right? So our final answer for this one is 0.9. Okay. Last one here. And we've got okay, hydrogen there. Once again, it's a methyl, right? So our base value is 0.9. And we look at the alpha position, the beta position. Okay. And then we don't have anything at a gamma position. You can kind of say that's the gamma position, but at that point, we're really just talking about we're already discussing that with, like, we could say there's a hydrogen kind of in the gamma position, but we're already dealing with this carbonyl being at the beta position. Okay, so what's at the alpha position? We just have R, right? So we're going to add 0. Okay, what's at the beta position? This is an R, so we add 0. But here, we have a carbon doubly bound to oxygen. and then also a hydrogen here. So we basically find the value at the beta position for an aldehyde, right? And we're told that at the beta position, an aldehyde will shift by 0.4. Okay, so altogether we have 1.3. Given that that is not listed here, it's probably 1.1 in terms of those answers. So the thing is that these values come from tables. So if someone else made this table, it may not be exactly the same. But theoretically, the idea here is that this is de-shielding, and so it should shift the ppm upward, but it's pretty far away, right? So the effect is actually going to be relatively small. And so, yeah, the effect of an aldehyde beta Yep. 0.4. So yeah, 1.3. So it's probably 1.1. That's probably the answer. If you have a table like this in your book, then it's going to be in your NMR chapter. It's going to look like this. Right, and then it's just going to have like OR, and then values in here, which tell you how much to add. Okay, so double check with your book and you may get something closer to 1.1.